exact ordinary differential equations. Say we have a first order ordinary differential equation in the form m plus n y prime equals 0, where m is a function of x and y, and n is also a function of x and y. Then we are going to create another function which we're going to call psi. So there exists psi such that the psi partially differentiated with respect to x is equal to m, and partially differentiated with respect to y is equal to n. If we can find our function psi, which is going to be a function of x and y, and equate it to equal a constant, then this will define y equals delta x implicitly, where delta of x is just a function. So this will be our general solution. That is a delta. So let's have a look at what our ODE actually is. So m plus n y prime. This is the left hand side. Now m is psi of x, n is psi y, and then y prime. So to write this out in a slightly different format, we've got del psi by del x plus del psi by del y, y prime. And y prime, of course, is dy by dx. This is equal to derivative with respect to x of psi, where psi is a function of x and del x. So we have substituted y for delta y, put that into here. If we have, or if we know that the derivative of psi with respect to x is equal to 0, then the ODE is exact. If it is not equal to 0, then the ODE is not exact, and we'll cover what to do in a further video. So let's have a look at an example. So we're going to solve x plus y plus 1 dx plus x minus y squared plus 3 dy is equal to 0. Sorry, not equal to 0. That's not in the question. So x plus y plus 1 dx plus x minus y squared plus 3 dy. The first thing we need to do is check that the ODE is exact. So we're going to take our equation and just rearrange it slightly. So if we divide everything by dx, then that will give us x plus y plus 1 plus x minus y squared plus 3 dy by dx. This means it's now in the form that we can recognise, so we can identify x plus y plus 1 as m and x minus y squared plus 3 as n. So if we take the derivative of m, partial derivative with respect to y, that will give us 1, and del n by del x is equal to 1. Because del m by del y equals 1, which is equal to del n by del x, then the ODE is exact. So we can solve it as an exact ODE. Okay, so from here we know it's exact, so we need to find our function psi. We know that psi of x is equal to m, which is x plus y plus 1. So if we integrate this with respect to x, we will find psi. So x integrated with respect to x is a half x squared plus yx plus x, plus we've got to remember a constant, but because it was a partial differentiation, it could be a function of y. So we're going to put f of y as our supposed constant. Now we know what psi of y is, because that is equal to n. So if we differentiate this function here, which we're going to call 1, so we're going to differentiate 1 with respect to y, partial differentiation psi. So psi of y, psi y is equal to, that becomes 0 plus x plus f prime of y. And we know that that is equal to n, which is equal to x minus y squared plus 3. Now obviously the x's cancel, so that gives us that f prime of y is equal to 3 minus y squared. If we integrate this to find out what f of y is, so this is integrating it with respect to y, that gives us 3y squared minus a third y cubed plus c. And from here we know that c should not be a function of x, because it was a function of y, so all is good. So now we can write that psi is equal to a half x squared plus y of x plus x plus f of y, which is 3y squared minus a third y cubed plus c. And that is the way to find the general solution of an exact ordinary differential equation. Thank you for watching.